All right, so today we have a presentation from my friend Lang Via on pressure meter testing in Clay Shales. Lang is currently a PhD student in the Geotechnical Engineering Department at the University of Alberta under the supervision of Drs. Rick Shalternick and Derek Martin. He obtained his bachelor's degree in safety engineering at the China University of Mining and Technology, followed by his master's of science degree in geotechnical engineering here at the U of A. His research interest varies from underground coal mining, hazard prevention, to petroleum and mining geomechanics. His research at the U of A is focused on pressure meter testing in deep sedimentary rock formations. This involves field measurements and analytical and numerical interpretation of the test data. Please join me in welcoming Lang.
Thank you, Kevin, for your nice introduction. In this presentation, I will go through some work we did regarding the application of a pressure meter test in Clay Shales. And just a brief introduction of pressure meter testing. It is a type of in-situ testing methods that have been used in geotechnical engineering since 1960. And there has been lots of research work done majorly in the last century regarding the improvement of the testing methods as well as interpretation theories. However, most pressure meter tests are in the shallow and soft deposits, such as clay and sand. And in this presentation, I will cover the work we did in the clay shale formations, which is at a much deeper level. So in the following presentation, I will talk about the motivation of this research and also give a brief introduction of pressure meter testing and the interpretation theories. Then I will go to the tests we did in the two sites. One is at the Cold Lake in Alberta. It is a cyclic steam simulation site owned by CNRL, and this test was performed in the clay shale caprock in a vertical borehole. And the second test series was at Monterey Rock Laboratory in Switzerland. Monterey Lab is an underground laboratory dedicated to testing a potential host rock for nuclear waste deposits. And after that, I will show some evidence about how those test results were affected by two anisotropies. The first one is Insatiable Stress anisotropy, and the second one is stiffness anisotropy. And the stiffness anisotropy can be intrinsic or induced by stress. Along with this, I will discuss some modeling techniques and interpretation strategies we applied to resolve those anisotropies. So first of thing is to, why do we do this? And the reason is because of the laboratory specimens are usually not representative enough because they has usually been disturbed through different stages of the sample handling and the preparation. For example, you can see here, during the coring, the stress relief likely induce the disking along the core, and during the also core storage and transportation, the moisture change in the environment will likely damage the sample by either desiccation or swelling. Then we also need to subcool the specimen from the core tubes and trim both surfaces to get it ready for the test. Those destructive work could induce more microfractures and even break the sample if not handled carefully. So the modeling studies in the operating clay shows that a specimen may suffer from a very complicated stress path from its in-situ state, and the structure tests in the on the operating clay, even for the specimens from the same borehole, shows this high variabilities of some measured Young's modulus, and therefore we think it would be nice to employ some in-situ testing technique as the less disturbed method to improve the assessment of the intact geomechanical properties of the ground. Another motivation of conducting pressure meter tests in the clay shale formations is to constrain the in-situ stress estimates in these deep formations. And the in-situ stress, especially the minimum in-situ stress, is actually an important factor in the assessment of the caprock integrity in SACD process for in-situ oil sands recovery, especially here at Alberta. However, the previous stress measurements, particularly by hydraulic fracturing, have shown a great uncertainty of the measured stress magnitude, even at the same depth. The uncertainty also remains in the stress measurements at Monterey. So you can see here from a paper published in 2003, two types of stress measurements, borehole slaughter and underground undercoring technique, have shown the big variabilities of the orientation and the measured. And so we think pressuremeter testing may be considered as another useful approach to provide an independent estimate for both magnitude and orientation of in-situ stress in the testing plan. So what is pressuremeter testing? There are different types of pressuremeter. The one I'm going to focus today is the pre-bored pressuremeter. And basically, you drill a pocket at the depth you want, and then you lower the pressuremeter probe into this testing pocket. Now you inject the fluid or compressed air to expand this probe under the controlled pressure rate. At the same time, and the expansion at different axes of the testing plan is measured by those calipers. So at the end of the day, you have the pressure readings as well as the displacement readings from those calipers. With that, we can plot this test curve and interpret the ground properties using different theories. So the theories that are generally used in interpretation is a cavity expansion theory. In this theory, the expansion is assumed to be axisymmetric, and there is zero strain out of the expansion plan. And these assumptions impose a constraint that every element in the radius will follow the same stress path, and the element in the ground will be under three principal stresses, like here sigma z, sigma r, and sigma theta, and it is subject to the mode called the plane strain shearing mode. And if we assume a zero volumetric strain, for instance, in the unstrained cavity expansion, the shear stress strain relation can be derived given the displacement and pressure measured at the borehole wall. And with those, we can have a complete stress and strain relationship by doing this in situ testing. And the concept of the cavity strain is defined here as the ratio of the radial displacement over the initial radius of the borehole. And furthermore, there is a prediction of the cavity expansion in elastoperfectly plastic materials derived by Anderson and Gibson for the expansion phase. And later on, Jeffries derived another solutions for the construction phase. And therefore, for a complete test, the solution can be divided into 4 phases: expansion before the yielding. You can locate this yielding point in your test curve, and the expansion after yielding, and also the contraction before yielding and after yielding. So by choosing right constitutive parameters, for instance here, the in-situ stress, shear modulus, and the undrained shear strains, the whole test data can be fitted by this closed form solution. And here it shows the test in the glacial clustering clay. We have this data from Seattle before. So now let's talk about the tests in Clay Shales. The first series of tests was at a thermal operation site, a cyclic steam stimulation site near Cold Lake. And CNRL has graciously provided us a borehole for this trial. And for test in the deep borehole, we have modified the pressuremeter from its originally from its base model originally made by Cambridge In-situ, and so it can be deployed with the wireline. And the picture here shows the wellhead with this 600 meters pressure hose, and the workstation including all the data acquisition and control systems, and the pressure assembly includes the expansion probe here in the downhole, as well as the downhole sensors, such as the temperature and the pore pressure sensors on the top of the pressure meter. We also have additional dead weights at the top of tool to provide the thrust force to allow the tool slide into this testing pocket. Because of the depth it has been deployed, we give it a name, reservoir geomechanical pressure meter. And the stratigraphy of the borehole is shown here at the left, with the 5 test locations in the Colorado group shales, as well as in clear water shales. The clear water shales are right above this oil sands reservoir, where the steam has been injected, and the clay shales, all of these clay shales were deposited in the Cretaceous age, and they are mildly over-consolidated. And from the previous laboratory investigations, they have relatively high porosities and also have low Young's modulus and shear strength. The data for the first test in the Wastegate Formation is shown here with the measurement by 6 calipers. And the hole, the testing hole is oversized and filled by mud. So the borehole expansion didn't start until the inflation pressure has exceeded the mud pressure. As you can see, this lift-off points here. And so with those 6 independent caliper measurements, we can convert the displacement reading into the average reading. And this black curves here shows the average test curve. And with this average test curve, we can interpret the ground properties using the cavity expansion theory. The shear stress strain relation can be derived using Palmer's analysis, and this shows a mild strength weakening after the peak stress, and also by an individual evaluation of the expansion and contraction phase of the data. We found out there is a degradation of the shear modulus from the expansion to contraction, which indicates damage might happen when the loading approached to the maximum pressure. The interpretation also performed by fitting the data with the analytical solutions, as I mentioned before, and a set of parameters including the in-situ horizontal stress and shear modulus and under shear strength can be derived from the best fit of the data. So another set of Pressuremeter tests present here are in Oppos Sk in Monterey Rock Laboratory. Oppos Sk is deposited in the Jurassic age and has relatively lower porosity and higher mechanical properties than the Colorado and the Clearwater clay shales. And the Monterey Rock Laboratory is located in Jura Mountain at the northwest corner of the Switzerland. And the bedding plan of the Oppos Sk in this lab has dipped about 40 degrees. And the first series of Pressuremeter tests were performed by soil experts, a contractor from Switzerland, and in the borehole BGC-2. And last year, we've been offered an opportunity to perform another 2 series of tests in borehole BGC-A4 and borehole BGC-A6. And borehole BGC-A4 was drilled perpendicular to the bedding plane, and the borehole BGC-A6 is drilled parallel to the bedding plane, and it follows the strike of the bedding. And so we're expecting different behaviors of the testing data because it was loaded with different orientation with respect to the bedding plane in these 2 boreholes. And here shows the example test data in 2 boreholes. The Pressuremeter is installed with an external accelerometer so that the orientation of the instrument can be determined. So this angle with respect to the top of borehole can be determined with the accelerometer reading. And for the test at the 9.7 meters in BGC A4, the radial displacement readings have a kind of abnormal behavior. You can see here from the arm 4 and arm 5, it starts to contract in the increase of pressure at about 12 MPa. And this is because of the artifact induced by the off-center movement of the instrument where the caliper arm sits during expansion. And we have proposed a procedure to correct this effect. And I will talk about this later. And the test in BGC A6 is less affected by this artifact due to its a smaller borehole size with a diameter of 76 meters. And so the deviation of the instrument body is tightly restricted. However, the test in borehole BGC A6 has a larger expansion, particularly in the arm 5 and arm 6, because of the higher compliance perpendicular to the bedding plane. Now we did the same thing to transform the data into a single curve with the averaged displacement reading. And because of the high shear strength of Oppos clay, we cannot see the yielding point even under the maximum expansion pressure. Therefore, the strength parameters can't be interpreted. One objective of this test is to evaluate the stiffness at different pressure levels. So we performed unload and reload cycles at multiple pressures and did the analysis for each of these unloads, both discretely and using the power law fit. So what we can see here is that the degradation of the shear modulus with the string amplitude, we can also see the trend of increase of the pressure on the increase of the material stiffness measured during the pressuremeter loading. And the stiffness becomes much dependent in the lower pressure level from 0 to 3 MPa, and it becomes less less dependent on the pressure loading from 5.8 MPa to the last under reload loops at 13 MPa, 10.8 MPa. And the dependence of this shear modulus on the pressuremeter loading was observed actually in all of our tests in this borehole. And this should be related to the stress-dependent behavior of the Oppos clay, particularly near the borehole wall, as I will further discuss in the later slides. So in the following sections, I will focus on our observations of anisotropy on the test results and some of the modeling techniques. I will go through and to show you how we can resolve these anisotropies with the proper modeling techniques. As mentioned earlier, the measurement by individual calipers of our pressuremeter doesn't necessarily reflect the true borehole deformation because of the artifacts of the instrument rotation, the vertical plane. Here it shows the shift of the instrument center with respect to the borehole center during inflation from 5 tests at the CNRL CSS site. A correction procedure is proposed here by applying elliptical fitting to the displacement readings at each pressure increment so that the reading can be transformed into a fixed coordinate system with its center being fixed on the center of the borehole. So otherwise, this artifact can be also cancelled out by averaging the readings at each diametric axis for example, on axis 1 and 4, one axis on 1 and 4, x 2 and 5, and axis 3 and 6. Here it shows the corrected profiles of the borehole evolving through the expansion for the tests in the Colorado and Clay Shales. And the first anisotropy we investigated is the in-situ stress anisotropy. And in this simple example, I show the elastic median under an anisotropic stress boundaries, sigma maximum H and sigma minimum H. And the stress distribution around the borehole can be predicted by Cauchy's equation. It's the prediction shows the variation of a shear stress with the angle theta here, and the subsequent unloading with a uniform pressure increment delta P applied to the borehole wall will not change this variation. So if the ground has a uniform ongoing shear strength around the borehole is likely yielded first under high shear stress in the direction of the maximum sigma H, and yielded later in the direction of the minimum sigma H. And the sequence of the yielding at the borehole will create the different expansion behaviors and the different orientations. So likely we will have the larger expansion in the direction of a maximum sigma H because of a larger development of the plastic zone in this direction. And we will have a less plastic expansion in the direction of the minimum sigma H. And this hypothesis is examined by a large-scale experiment conducted in the polyaxial loading facility by CNPC in China. We cast soft cement blocks and install the pressure meter in the center hole. Then the boundary loadings were applied by hydraulic flag jacks at the side. So we have tested 3 different stress ratios, sigma maximum H over sigma minimum H in 3 blocks, and it confirmed the larger expansion. As you can see, the red dot line here has larger expansion after yielding. It is aligned with the direction of the maximum maximum horizontal stress orientation. And in the increase of this stress ratio from the 1.12 to 1.94, the difference between the expansion in the axis of the major and the minor horizontal stress also increases. So we validate this hypothesis, and now we can model the borehole expansion using the numerical technique. So here shows a model under the plane stress condition with 2 boundary loadings. Here we predict the large scale experiments we did in China. We perform the analysis assuming an elasto perfectly plastic behavior for the tested cement, and with the boundary stress applied in the experiments, the prediction curve applied and the prediction curve have agreement with the measurement from the experiments. And now, how can we apply this modeling approach to the in-situ stress determination with the field data? And this can be done in an inversion process. Basically, what we did is to try different values of the maximum horizontal stress and the minimum horizontal stress in the model, and iterate this simulation again and again until the misfit between the computational curve and the test data is minimized. So the whole process was coded in the MATLAB using an optimization approach. Here I can show you an example of how this inversion process works. So you can see the misfit is minimized through about 30 steps iteration, and it found out the best fit, model fit for the test data from the Colorado Clay Shales, and we compared this derived anisotropic stress from our best fit with the in-situ horizontal stress determined using the traditional cavity expansion analysis I mentioned earlier. It is encouraging to see that this average value falls into the range of the maximal horizontal stress and minimal horizontal stress. And borehole expansion is also influenced by the structural anisotropy of the clay shales. The structural anisotropy is majorly from the bedded clay particles as a result of the deposition, compaction, and diagenesis and other geological processes in the history. Here it shows for the Oppos clay, the laboratory tests shows the elastic modulus in the direction parallel to the bedding will be up to 3 times higher than the direction normal to the bedding. So for a borehole drilled with an arbitrary orientation with respect to the bedding plan, the symmetry of the elasticity in the testing plan may not exist. And this would lead to the anisotropic deformation when we're doing the pressuremeter test. So how would this affect, for the test in borehole BGC-A6 at Monterey, the pressuremeter loading is partially against the bedding. The impact of the structural anisotropy can be identified by comparing the borehole stiffness at some varying axes in the testing plan. Here, a nominal shear modulus value is determined by applying a simple linear regression on the unload reload cycles for each axis. And then we plot them together. It shows the higher stiffness parallel to the bedding than normal to the bedding. And this polar variation of a stiffness G star remains almost the same at the higher pressure range. It might indicate the dominant impact of the bedding plan beyond the damage zone near the borehole. So to determine the structural anisotropy, there is a closed form solution derived by Amadei and Savage for borehole expansion in an arbitrarily anisotropic medium. For the special case we have here, where the medium possesses the transverse isotropy, 5 independent elastic parameters are required. So by choosing the reasonable values for these 5 parameters, the polar variation of a borehole stiffness from the pressuremeter measurement can be fitted by the model solution. And the stiffness anisotropy could also be induced by the local stress concentration around the borehole after unloading. When high deviatoric stress is present, extensional fractures parallel to the borehole wall might be initiated, and this would lead to the reduction of a stiffness. The induced anisotropy after unloading was also shown in another geologous claystone in the underground laboratory in France. They did the tomographic analysis of the ultrasonic velocity survey. It shows the low P-wave velocity near the axis of the minor in-plane stress, and it confirms the damage that might happen as a result of the local stress concentration and such a direction. And such anisotropy was also observed in our tests in borehole BGC-A4 when the loading is parallel to the bedding plan. At the lower pressure range of the loading, the polar variation of the borehole stiffness has its minor axis preferentially aligned at the angle about 0 degree, which indicates the greater damage in such a direction. While at the higher loading, this anisotropy disappears, the variation becomes more isotropic, and the measured stiffness now is dominated by the intact rock behind this damage zone. And the interpretation of the borehole expansion in a damaged medium requires more modeling efforts. And the first thing is to understand how this damage occurs and how it involves. And here it shows the stages of microfracture development under UCS test of Oppos Sk. And in this particular test, and they monitor the acoustic emission and from the beginning of the load until the post-peak stage. And the acoustic emission activities emerged at a very early stage of shearing. And therefore, the crack initiation might happen at a very low evatoric stress. It also shows that the acoustic events stop to accumulate immediately after the peak stress, which means that the damage might reach its limit. So with evidence like this, the damage initiation and the evaluation criteria can be formulated constitutively. Damage variable D here is introduced to characterize the degradation of the stiffness and assume it has a variation with the equivalent string measures. Here, epsilon hat. This string measure can be a plastic string or total string. And Dr. Parasio from EPFL has built a model, a plus damage model, and verified with the laboratory experiments. He then implement this model in the finite element analysis to simulate the damage around the circular excavation in an anisotropic stress field. And the next step is to model the pressuremeter loading in a damaged medium. And it is believed that the observed borehole stiffness increase is associated with the closure of those induced microfractures around the borehole. So using the same continuum damage mechanics technique, we introduce a recovery variable Q to define the stiffness recovery under stress. Likewise, the stress-dependent recovery function is also proposed here. Then we implemented this into a finite element model, and in this case, it is an axisymmetric model under isotropic stress condition, and the radial variation of a degraded stiffness after borehole unloading could be predicted. The stiffness recovery after the pressuremeter loading can be also predicted in the second stage when this internal pressure is applied. As well, we also predict the shear modulus from the expansion curve from the simulation, and it has the trend that agrees with what we observed in the field. And now we're working on to extend this analysis to the anisotropic boundary stress condition. Alternatively, the whole damage and recompaction process can be also simulated using the finite and discrete element model, like here showing in the paper published in 2016. And in this modeling, it allows the extension path of the cracks and the separation of buildings to be predicted after excavation. And by applying the internal pressure, the closure of those induced discontinuities can be also simulated. It provides a good platform to simulate this cyclical process of microfracture initiation and closure. And some other in-situ measurements were also used to inform the borehole damage zone. For example, in this case, the seismic survey can be conducted locally inside of a borehole. So Dr. Schuster previously from BGR, and they developed the probe with multiple receivers with varying distance from the emitter, and the velocity of the wave penetrate into the borehole wall can be measured with this tool. And by rotating this probe, the anisotropic information of the velocity in the cross borehole plane can be also obtained. And this may be further used to produce the velocity contour, like the one I showed earlier for the borehole damage zone identification. And of course, this is not complete and needs more research work, particularly for the calibration of the constitutive model. We need to conduct laboratory tests that can present the stress strain path at the borehole during unloading and the pressure interloading. However, the disturbance of the laboratory specimen is always a concern, and this actually needs to be taken into account. This needs to be considered in the steps of the constitutive model verifications. And the other independent field measurements, for example, on the borehole seismic survey, are also useful in informing the initial condition of the test, and also the uncertainty of the in-situ and near excavation stress field may be reduced by performing in-situ more in-situ stress measurements associated with the stress modeling around the excavation. However, each of these independent measurements require the skills of the specialists, and combining these measurements in the same assessment work with the pressuremeter testing data would help us constrain the in-situ condition of the ground, especially in such a complicated environment at Monterey. Here it concludes my presentation, and before I go to the Q&A session, I would like to acknowledge the guidance from my supervisors, Dr. Rick Chanatonic and Dr. Derek Martin. I also appreciate the valuable opportunities from CNRL and Langua to allow us to have this field trial of pressuremeter tests at their site. I also would like to thank the colleagues from my group, Visible Geomechanical Research Group, for their support. And thanks goes to CMPC for their help in the large-scale pressuremeter experiments in the soft cement. Particularly, I will mention the field crew for those tests in CNR tests, Dr. Nathan Desman, and Anil, Kais, Sebastian, Dongming, and for Monterey tests, and also Dr. Nathan and Kevin for the help on site, and also appreciate the on-site assistance from those service company for the CNR tests, and the help from Swiss Topo and this drilling company for the Monterey tests. I also like to appreciate the valuable input from Cambridge In-situ, a pressuremeter company in UK, for their advice in operation and the improvement of the testing technique. And this research is financially supported by Energy Simulation Industry Research Consortium in Reservoir Geomechanics. Here shows the references I covered in this presentation. And if you are interested in learning more, you can check them out. And with that, I would like to say thank you for all your attention. And now I'm happy to respond to any questions you have.
Thank you, Lang, for your excellent presentation. Thank you very much. And now we have a few questions for you. Let's get started. So from Anna Menderson, she was asking about the overcutting you mean on slide 12, but Dr. Rick answered here real quick for us that overcutting refers to the degree of oversize of the borehole relative to the diameter of the pressure meter tool. But if you wanted to add something, please. Lang, I guess you were on mute.
Oh, sorry. Yeah, now I'm looking at it. I look at the question, the overcutting. Yeah, so maybe it's better to go back to that slide. So the borehole actually is oversized because you have to, the borehole has to be bigger than the Pressuremeter diameter for the entry of the tool. However, this has an influence on your interpretation because usually, sorry, I can hear some noise from the background. I moved from here.
Guys, any one of you are unmuted, please mute yourself.
Yeah, anyway, so the ideal condition is that the borehole size has the same size of the Pressuremeter, and then it will match the analytical solution pretty well. But in the reality, we have the size of borehole bigger than the tool. That's why we have to consider the effects of this initial condition into our interpretation.
Yeah, okay, thank you. So moving on, Andres Puerta Mejia have a question about if you can say that results are clay content dependent. Do you know if it is possible to say that?
I cannot make a conclusion here because the clay content I show for these two clay shales you can see has a very big variabilities because even in the same region, in the same materials, you may have the strong heterogeneities regarding the mineralogies and also regarding the compositions of materials. So yeah, this has to be done individually with the individual specimens. Yes, I think roughly you can see the mechanical strength is correlated with the clay contents, but it has to be very case specific.
Okay, he has another question here about what makes Pressuremeter different from any other in-situ techniques such as hydrofracturing?
So Pressuremeter testing is different from the other testing because it does not only provide the results from a point load, it's like the CPT or SBT. You just like push the tool through the ground, and the Pressuremeter testing is conducted in a way that the full stress and strain curve can be obtained. So it does not only provide information at a one stress condition, it provides information of the constitutive behavior of materials along the stress path. So it can be interpreted with the well-established cavity expansion theories and can be compared with structural testing data along its stress path. So I'm not sure if I answer your question, but yeah, I think the major advantage of Pressuremeter testing is that it provides a full stress path for the materials under the stress condition.
Okay, thank you. So Anna Manderson has another question about unload and reload loops. She was asking if the quantity of unload reload loops affect the data. Would fewer loops for the same pressure range have provided better data?
So the answer is no. So by theoretically, the unload reload is conducted in the elastic condition because you relieve the stress. So even sometimes we see here, the materials entered into the plastic phase, but it's doing unload, basically go back to the elastic phase. So this unload reload loops basically remain in the elastic phase. So once you load it back, ideally you should come back to the point where you start unload. However, the discrepancy here is because of the whole test. Basically, I haven't described this And basically, we kind of stop further loading the pressure meter and keep the pressure constant. But this whole test is not successful, so you can see the pressure drop. So during this process, let's say 5 minutes or 10 minutes, you lost some excess pore pressure and you change the material behavior. That's why when you reload it back, it doesn't click to the point you unload. But ideally, it's supposed to be go back to the point you unload.
Okay, thank you. Daniel Cartagena has one question here. If there's any limitation in the use of this technique in horizontal wells, horizontal boreholes?
Yes, for sure, there's some limitation. I'm not expert in downhole tool, but I think to deploy this tool into horizontal well, there might be some restrictions. It's not as straightforward as deploying in a vertical hole. And another limitation in terms of interpretation, I think it might be related to the orientation of the bedding plan, like I showed in these slides. And considering the stiffness anisotropy would help you better interpret the data.
Yeah, that's true. Another question here for Andres Puerta Mejia. He was asking, he was mentioning that, as I understood, experiments were done in unfractured media. How could such situation affect results?
That's a very interesting question. We're always trying to say how the local fractures would affect the radial displacement measured during the inflation. But we never really have done such whether the physical experiment or numerical experiment. From what I can say from my previous experience, there are some data showing the abnormal behavior that might be affected by the fractures preferentially crossing the borehole. There are also evidence from our core logging that there is some, they say, the fault plans dipping through the borehole, and we use that as evidence to explain this abnormal behaviors observed in the pressuremeter testing data, but so we never systematically done any analysis on that.
Okay, so moving on, Anna Menderson has another question here. She was asking if you use a self-bottom pressure meter to check your finds on slide 22.
So I think the reason, I think I would rephrase the question that the interpreted sigma maximum age and sigma minimum age agrees with the interpretation from a test by self-boring pressure meter. The short answer is no, because we didn't done any self-boring pressure meter in that borehole. And from what I know, I think there's also some great difficulties in using self-boring pressure meter in interpreting the in-situ stress, because no matter how perfect the borehole you drill, it will be more or less affected by the disturbance of the borehole wall, which will provide the same situation as we did in this test. So we didn't do that test, but I'm afraid that the self-boring pressure meter could provide better results.
Okay, thank you. Dr. Rick is praising the questions, really like these questions, outstanding. And Andres Puerta Mejia has another one. He was asking if you could explain in the later results why AE didn't increase despite large strains. And he was mentioning that, in fact, they kept constant for a while. What could it be causes?
That's also a great observation. So as you can see, that's when the stress reaches the peak stress here, and we have a very sharp reduction of the strength, now it keeps into a plateau at the post-peak stage. If you look at what happened on the sample, you found this period, this moment is actually when the rupture plan was formed. So before that moment, it was, I think it was just microfracture initiation and development. But at this moment, all the fracture were combined, were coalesced, and now formed a big microfracture, which is the rupture plan. And after that, the post-peak behavior is more dominated by the sliding of the rupture plan instead of the further development of microfractures. That's why the acoustic emission signal stopped to accumulating after that point.
Okay, thank you. So one more question about Junko. I don't know if I'm spelling her name correctly. Sorry about that. Thanks for this very nice presentation. I wonder if you could estimate or fit all the coefficients of the compliances of or stiffness tensor with this methodology.
Yeah, that's a hard question to answer. So usually, yeah, I know this question is from Abel. He's an expert in the elasticity isotropy. I don't know if I think that we have to have a good environment or good test condition to investigate the stiffness tensors, because if you're just doing Pressuremeter test, the loading condition is limited, basically on the cylindric cavity expansion. It doesn't provide enough information for you to constrain the full elasticity tensor. But I think if you have opportunities to do more tests in different orientations, there might be a chance for us to look at how the borehole expand in different orientations in the ground, and may give us some information to estimate the stiffness tensor.
Yeah, Dr. Rick said, interesting concept, Abel, something definitely to think about. And Andres is thanking you for answering his questions. So an excellent Q&A today. Thank you guys for your questions. Thank you, Leng, for your answers. And do you guys have any other questions? Because we are about to finish this session in 5 minutes. No, I don't think so. So thanks. Thank you, Leng, another time for your excellent presentation. We had an excellent seminar today, and I hope you guys enjoy it as much as I enjoy it. And I see you next week. Thank you, everybody. Let's finish the session here.